Let me continue from the place where I had left last. The source material, as I said, is important, and then I acknowledge fully both CRC Press and Rensburg's contribution. And we should understand that as one of my colleagues has explained, over so many years these things have been formulated, and then in cases where it is fully analyzed, it is very much what do you call possible to calculate things. So, most manufacturers will directly give you from the whatever the source, the junction, all the way up to the case, and in where the specification of the small heat spreader is given a little to the next level. So, if you see, if you come to this end, I will quickly go through these and tell you a little about. If you check these, for example, there is a what do you call an institution called the JEDEC, sorry for my accented pronunciation, probably you can make out it is. This JEDC stands for Joint Electronic Devices Engineering Council. So, this engineering council over maybe I am not very clear, but over 50 or 60 years have standardized various types of packages, and most packages you have a way of going back, and you can always ask them, no, saying can I become a member, and you are welcome to become the member of it. Now, you see here, if I go, you are allowed to become a member, and you can also add any new package which you have done with the various other type of things. Having said that at that point, and then I will try to show you. We have this beautiful what do you call data directly given by the manufacturer. One of the simplest thing is, if you have a package like typically your integrated circuit and so on, very rarely we attach a big heat spreader on top of it, except in the case of well known devices. So, they have given when theta junction to ambient such as specified by JEDEC, and then they have given this is engineering association series of documents. So, we have what do you call literally from the horse's mouth on a lot of this stuff about thermal metrics for semiconductor integrated circuit packages ranging from to this thing. Metrics are misapplied by those who try to use them to estimate junction temperatures. This document describe traditional and new thermal metrics to put their application in perspective with respect to system level junction temperature estimate. You see here, original thing has been prepared early 2000 and we are late 2010. So, various things including junction to moving air and industrial and commercial temperature ranges and large number of these things are already listed here, which it is very what do you call encouraging. Industrial temperature ranges, it looks like minus 42 plus 85 degrees centigrade is used occasionally. So, are we likely to face AC 85? Yes, maybe as you said, directly if you go into the automobile, and then inside the automobile we have the engine control unit, ECU. So, it is quite hot, it is hot under the hood. So, they have given system level thermal design is required to ensure that the maximum operating device temperature not exceeded even when the input ambient air temperature is between minus 40 and 85 degrees centigrade. Now, coming back again to this, they have the other thing saying commercial temperature ranges. Commercial temperature range function at ambient temperatures of 0 to 70, which by our standards is very benign, quite benign, because 0 is something maybe external freezing, and then 70 is what we are likely to face most of the times, even at homes inside. If you have a closed box, take for example a microwave oven or that new clothes washers and dishwashers. Some of the clothes washers use 90 degrees centigrade hot water, and the inlet is often from the hot water that is available for room heating. You have a centralized huge boiler, sometimes it is depending on where you are, very rarely that main thing is electrical. It is based on furnace oil or some oil which is used. Basically, they are oil fired boilers, and then hot water is available, and that hot water usually 70 to 80 degrees centigrade which is there. And now currently solar water heaters are available, rooftop water heaters. Once you have a solar rooftop water heater, and in a semi commercial or group establishment like a hostel which you are likely to be familiar with, or in case you have a home slightly remote and not stuck up in an urban jungle, you have vast area of rooftop available, and then using a normal what you call rooftop, not PV. When we talk about generally about solar water heaters, it is not a PV water heater, it is a simple static this thing, and occasionally pumping may or may not be there, but generally it is a just an inclined plate encased in a greenhouse tank, and then depending on the radiation, and we in India we come under the zone 2. Zone 2 is not really hot, it is a little hot and not very hot, not like zone 1 which is probably in the desert areas. So, even here 60 to 70 degrees centigrade hot water is available. So, if that is fed into the either your dishwasher or the clothes washer, all electronics must be capable of dealing with this 70 degrees centigrade. That is why it is. And when proper care is taken to ensure these things, so we see here the manufacturer invariably gives us various details about how to measure various temperatures, and this you see here very beautiful thing. We have a cold plate outside, coolant in to maintain the temperature in which we maintain it, and you see here there is a nice thermocouple. Advantage of a thermocouple is it is a very small contact area, and then not much of heat load is placed on that. So, you have seen this fine wire thermocouple is glued or soldered to the device pin closest to the die. So, it is possible for us to on a hot die. So, we have such a big, we have a board, then we have calculated, and then we have an ambient node, ambient what you call resistance, surface, and then calculated, measured, and so on. No? So, we have various way of calculating junction to board temperatures and so on. So, we have a heat sink, thermally conductive epoxy, then there is a package how these things are mounted and so on. Using all this, the manufacturers have made a lot of these data available to us designers to use it. They themselves probably use the modeling and the analytical methods which are described in the main lecture. So, if you just search around on the what you call in your on your internet and all the other things, we have beautifully, you have seen this, a beautiful correlation with which it is very much possible for us to knowing the correct conditions. If you know the power and if you can somehow estimate all these various type of junction to ambient, junction to case, case to heat sink, sink to ambient, all these things, it is possible for you to get approximately, very close to the junction temperature, which is good, absolutely, which is very good. And the manufacturers themselves, I will now try to minimize this and see. You have seen this here, there is conduction here, there is a conduction here, and then there is conduction directly to ambient, and then you have something through the leads, and we have a huge collection of. This is taken from one of the manufacturer's catalog. You see here we have a beauty saying the TO3 is the conventionally, which I have were trying to explain to you earlier, is the so called power transistor, that case which was in use for a very long time. So, it is about this much size, I am sure some of you have seen it, and if you are hobbies, you would have seen these old power transistors including several switching transistors. If you have a audio amplifier, it is possible if you are operating in class D, get tremendous amount of power and then make it little more efficient. So, all of them invariably use this TO3. TO3 is a very nice what you call, you have a beautiful base which is made of high conductivity material, often a variant of copper. Then in this also now you have two variants, you have the 2 lead and the 4 lead. Now looking at the what you call the thing here, you have seen this here, junction to case is 3 degrees centigrade per watt. So, if somehow the case can be kept around let us say 40 or 50 degrees centigrade and you have 10 watts, you are still at inside the case, the junction can be 3 into 1030 above the case. So, if the case is at 40, you still nicely you can get away with 70 watts, and then a little going up higher and higher, if you can tolerate around 100 degrees centigrade of the junction, and then the the case is at as I told you, I will take an example of 40. So, you still have 60 divided by 3 safely 20 watts can pass through it. Now, the 20 watts refers to steady state after the temperature has stabilized over a measurement time. The right side figure shows you the actual directly junction to ambient if you do not have a heat spreader of any type. This one refers to junction to case when the case can be maintained at a given temperature. This is directly junction to ambient. So, if the ambient itself is again taking that old example of 40 degrees and then you have this 35 degrees. Now, the amount of heat that can be allowed to be dissipated will become 10 times less. You understand, no? Between 3 to 30. There 30 degree centigrade rise, and here it is only a 3 degree centigrade rise with a, I will now start using the word heat sink. With a heat sink, what gets 3 degrees for a given what do you call watt. Without the heat sink, it can become so much. Some of you would have seen the old transistors which come in a metal can, well known TO5 package. So, you have seen here, if you put a small heat spreader, you can come to 40, and then if you do not have a heat spreader directly, it becomes very, very high. So, it is not possible for you to next I would like to point out these things when I get back to the PowerPoint projection again, try to show you these things again. You see here at the top, I am sure several of you must have come across this TO 220 packages. TO 220 instead of the old TO 3, the same what do you call die and chip is mounted in a plastic case. You understand, no? Plastic with a small heat sinking what do you call base attached to it. So, what was 3, it is like it suddenly becomes 4 times as much, because the amount of area available for contact is much less. So, you have 3 lead, 5 lead and so on, no? Typically all of them are same. Once again we end up with the same condition. If you are not to use any heat sink, it is as good as that same old TO3 package. And then as we go on, so many of them now have been, so many new packages have come about. So, we have these SOT packages and all that, which is not intended for power applications, and all the time manufacturers are coming back with more and more newer type of packages all the time. Now, I will start with the little bit of allow me to get back to the what you call background material. So, this typically here you will see that you have seen this, no? There is at least one interface where heat flow must cross between two surfaces. Very rarely things are directly built into it, except maybe a heater or these are what do you call electronic lamps, where there is an arc lamp and so on, where directly the final effect, the gas heating and all, it occurs directly by various electrical and heat phenomena. In this case, in all other cases normal electronic thing, we must have an interface where heat flow crosses two surfaces. At each interface is a measurable temperature difference across the joint. This is the boon, this is where we can work completely. You understand, no? There is this thing. This can occur dramatically within two rough surfaces under light joining pressure, or slightly in the contact between device soldered to the heat sink. You understood, no? But it still exists. Even if you are to directly take a electronic device, the base, and use some way of as a soldering usually has an interface material. The other is directly welding. You can have contact welding, that is you can have electrical resistance welding. Other than that, you have also sometimes the same thing is called brazing or hydrogen brazing. You put it in a inert gas and then pass another this thing, and the whole thing, no, they get fused much better. But even then there is some temperature drop and some resistance. Each of these contacts contribute to the overall thermal contact resistance. Additional resistance can cause excessive component temperatures. This is where it is. Estimate that when you join seemingly identical cross sectional area components, this is a very, very critical thing. 5% of the apparent surface actually make intimate physical contact. You have seen that, no? In the very early beginning of the lecture I told you, even the so called metal to metal, that is, if you take a let us say 10 mm by 20 mm T/220 back of it, and then try to attach it to another 10 mm by 20 mm what do you call a copper rod, and try to conduct it. Very little of it, in fact, this is to me it feels threatening. First time I thought it could be 50%. If we just slightly just touch it each other, no, only 5% of it is actual contact. Remaining, there is always some other medium in between. Subsequent slides explain to you. We cannot ignore thermal contact resistances, but they are very difficult to quantify. No accurate models exist that are applicable across a range of packaging applications. So, when they talk about packaging applications, latest is you would have seen all these new high power diodes. If you take a so called 3 watt white LED, 3 watts is a lot of wattage, and then the actually light emitting area of the chip LED may be less than 1 millimeter square. Now, if you go and examine lec11 star LED by either Philips or Osram or any of these people who make LEDs, you see that all of them know, and one of them well known thing is called Golden Dragon, GD LEDs and all that. You notice that it already comes pre-mounted on a chip, I am sorry, on a small octagonal or hexagonal heat sink area. Understand, no? That is, somebody has braced it. Alternatively, if you buy the chip LED and then the way they put it in your commercial things, they give how the pad should be, how a slug in the center should form its thing, how the whole thing has to be used in the application note. Again, coming back to this thing, no accurate models and so on. Next thing is, instead, can we have a simplified contact resistance? Consider that heat flows from a microprocessor into heat sink, both of which are in intimate contact. We assume that heat flow occurs in the axial direction x only. Heat flows through the microprocessor according to Fourier's law. This I said is what was made 200 years back. What he has found out is if you increase temperature, more heat flows, and then a lot of it is related to the area, and then we have a proportionality constant. And then the inverse of the proportionality constant, we use it directly as a thermal resistance, where the advantage if we can add up these things. In a real interface, surfaces are not perfectly smooth. As heat flows from the microprocessor into the heat sink, the heat transfer area seems constant. We call that the apparent contact area. We call the temperature difference caused by this thermal contact resistance. We call the interface coefficient Hi. Apparent contact area is composed of the cross sectional area where we make actual hard contact, and a void area of contact does not occur. The apparent area of contact then is the sum of both actual and the void area. Magnified view is given in this model. Have you seen this? So, we have a material A, material B, and then in between, no, is there something we can do to ensure the isothermal lines getting here? All this air no has no practical what do you call thermal conductivity. Without interstitial material, with interstitial material greatly increases the contact area available for heat transfer. In a lecture, a few lectures earlier, I had given you the heat conductivity of both air, water and so called heat sink compound. Usually they have that leaded paste. It is not very high, it is still, well, if you take one for, I mean, some 200 for copper, this comes nearly 0.2 or something, 1000 times less. So, if you can somehow make this 0 and then do something else, subsequent lectures will give you, I will come back, you see here.